Hello, I'm Kai-Yan Zhao from Purdue University. Today, I'm going to present on-demand fork, a fast design and implementation of the fork system call. A lot of us interact with shells every day. If I type in Vim in the bash shell, the Vim text editor is started for us. Behind the scene, the fork system call is used. To recap, the fork system call on Unix-like systems creates a child process by duplicating the calling process's kernel state, including virtual memory, file descriptors, permission, etc. Traditionally, fork is used to run a new program. For example, when a user types Vim in a bash shell, bash creates a child process with a fork system call and then runs Vim using another system call, exec. Fork has many more modern uses than simply running a new program. Applications also use fork to clone a process instance. For example, buzzers and testing frameworks use fork to take test inputs. Serverless frameworks use fork to run Lambda functions serving user requests. Databases use fork to take snapshots. These applications, unlike shells, can have significant memory footprints from megabytes all the way to terabytes. Fork might be fast enough when allocated memory is no more than a few megabytes, but with increasingly large memory footprints of applications, fork is getting slower. How slow, you might ask? At 50 bytes of allocated memory, a fork call can take over 250 milliseconds on average to complete. We will look into why fork becomes slow in a moment. But first, let's see how bad is this 250 milliseconds of latency. The high latency of fork is detrimental to latency-sensitive applications. Take Redis and in-memory key value store, for example. It supports persistence by taking snapshots and periodically calls fork to take snapshots of its data. But during the fork system call, which will last a very long time if the database is large, Redis is unable to serve any user requests. In the meantime, requests from users just keep queuing, resulting in noticeable latency spikes. Fork call blocks Redis from handling user requests, and just like Redis, there are many other applications that call fork on their critical paths. Such high tail latency caused by fork is unacceptable in many latency-sensitive settings. Fork also has an efficiency problem. During the fork system call, the entire address space of the child process is set up, but some applications only access a small portion of the memory in the child process. For example, when an application is being fuzzed, most of the input will exercise the application's error paths, and executions will mostly be short-lived. As a result, most of the work of setting up the address space of the child process will be wasted. We want to know, why does fork have the latency and efficiency problems, especially when the size of an application get large? The answer is that fork provides distinct address spaces for the parent and the child processes by copying page tables from the parent process to the child process. As shown in the diagram here, page tables are structured as the tree and have 4 levels typically. Each level has typically 512 times more tables than the upper level. The more memory a process consumes, the more page tables it has, especially on the last level. This might be fine when applications only use a little bit of memory, like shells. But as memory gets large, the tree will get fat, especially on the 4th level, or we call the last level. This makes copying the entire paging tree prohibitively expensive. Copying page tables will progressively get slower and dominate the cost of fork. In fact, the cost will be linear to the size of allocated memory. People have attempted to use huge pages to speed up fork for large applications. What happens is that instead of having 4 levels of paging tree, the huge page is described by a 3-level tree. For a given size of allocated memory, larger size pages are fewer in number, meaning fewer page tables copied during the fork system call, therefore faster fork system call. Huge pages can lower the latency of fork, but suffer from the following problems. A page that is over 500 times larger is more likely to experience internal fragmentation and takes longer to copy in a page fault. Also, finding contiguous physical memory large enough to form a huge page also takes longer, causing system-wide latency can In fact, if you Google huge pages, a very common question people ask is how to disable huge pages. Can we have a solution that is compatible with fork, but is faster and more efficient? We propose on-demand fork, a novel design and implementation of the fork system call. On-demand fork only copies top levels of page tables and shares the last level page tables during the system call, therefore avoiding the cost of copying them. On-demand fork can substantially reduce the fork system call latency, achieving microsecond level latency for up to 50 gigabytes of memory in our experiments. On-demand fork does not suffer from issues plaguing huge pages, such as fragmentation and pulses. After a call to on-demand fork, if the application reads from a memory address, the access goes through by translating virtual addresses using the dedicated top-level page tables of the process, and then by shared last-level page tables. This means that applications using on-demand fork won't incur cost of copying page tables for read access. There are several challenges involved, one of which is to preserve the copy and write semantics of the traditional fork. Copy and write refers to the rule that the parent and the child process after fork have the same view of the memory, but changes to memory are not visible in the other process. This is achieved by disabling the write permission in last-level page tables during the fork system call. Here we use a simplified paging tree to illustrate this. But if either of the two processes try to write to memory, the process will trigger a page fault and get its private copy of the physical memory page, and the corresponding page table entry will be updated. On-demand fork disables the write permission in the second to last level page table entries, utilizing the hierarchical attributes capability of common architectures to control the write permission of the entire region mapped by the last level page table. Because processes may eventually write to memory after on-demand fork system call, which necessitates updates to page table entries, unshared or dedicated page tables may be required eventually. So on-demand fork copies page tables on demand during page faults. The rule is that there are page faults for write access only. The page fault handler checks whether the last level page table is shared. If so, it makes a copy of the shared last level page table for the faulting process. It then proceeds to handle copy and write of data pages. Notice that the increased cost due to copying of a page table in the page fault handler only exists for the first write access to each 2 megabyte region after fork. Now that we have an understanding of on-demand fork, let's look at how it performs. We tested on-demand fork with micro-benchmarks on system call latency and page fault handling time. For system call latency, we measured the time it takes to call fork and on-demand fork for a process with different allocated memory sizes. We show that on-demand fork runs 65 times faster than the traditional fork at 1 gigabyte of memory. On-demand fork runs 270 times faster at 50 gigabyte of memory. Also, on-demand fork runs faster than using huge pages with the traditional fork. Because on-demand fork may have to copy 1 page table plus 1 data page when handling a page fault in the worst case, we want to make sure that its page fault handling time is reasonable. From our experiments, on-demand fork has 5.3 times longer page fault handling time in the worst case, whereas huge pages take 86.3 times longer. Recall that the worst case of on-demand fork happens only during the first access to each 2 megabyte region after fork, and subsequent memory access will not incur additional cost compared to the traditional fork. On-demand fork delivers much faster system call latency while keeping page fault overhead acceptable. On-demand fork benefits real-world applications by reducing fork latency. As we have discussed earlier, Redis is a key value store that calls fork on the critical path when taking snapshots. In our experiment, Redis is initialized with about 1 gigabyte of data and takes snapshots periodically. Comparing fork with on-demand fork gives Redis a 98% lower fork latency when doing snapshots. When measured from the client side, on-demand fork gives Redis a 65.95% lower tail request latency at 99.99 percentile. This improves the responsiveness of latency-sensitive applications and helps mitigate high tail latency in data center settings. On-demand fork also benefits real-world applications by increasing throughput. We tested American Fuzzy Lob, or AFL, to demonstrate this. AFL is a coverage-guided fuzzer that instruments the target application, which is SQLite in our experiment, to execute to a customizable point in its code and repeatedly calls fork to take new inputs. Comparing when using the traditional fork versus on-demand fork gives AFL a 2.26 times higher fuzzing throughput. This allows bugs to be found sooner during a fuzzing campaign and improves the cost effectiveness of fuzzing as a bug finding method. In conclusion, the traditional fork is slow, whereas on-demand fork is low latency and efficient. It's low latency because of deferring work of copying page tables from the system call to the page flow handlers, and it's efficient because of performing the work of copying page tables selectively. From our experiments, we show that on-demand fork is up to 270 times faster than the traditional fork. It gives Redis a 65% lower tail request latency, and it gives AFL a 2.26 times higher fuzzing throughput. It is also our hope that on-demand fork and its characteristics will enable novel design in software. Finally, you can find the source code of on-demand fork at the GitHub link below. Thank you.